Yes. Okay. So now that we defined potential energy and of a conservative force, let's extend this and relate potential energy and kinetic energy, right? So we know that by the work energy theorem, F net done on an object is equal to the change in kinetic energy. Here we call it kinetic energy K instead of KE, like we did in the last chapter. That's just how the book, I'll follow the book from now on. And we also found that the change in the potential energy is equal to the negative F net. When we combine these two equations, right, we get, sorry, should be just that. This is equal to the negative KE. And we bring it over to the other side, and we get the change in kinetic energy plus the change in potential energy is equal to 0 for conservative forces. And think about what this says, right? So the initial state, right? So let's define what that is. So here we have the final state minus the initial state, and here the change in this is the final state minus the initial state, right? What this says is that whatever change in potential energy can be accounted for in the kinetic energy, right? If there's a change in the potential energy, that means there's the opposite change in the kinetic energy because they have to sum up to 0. The changes have to sum up to 0. And this is the mathematical formula for conservation of energy. Energy cannot be created or destroyed. It's like money. Think of money. You collect a certain amount of money. It's like you gain an energy and then you hand it out. It's always accounted for, right? The Treasury always counts for every dollar and cent that it gives out to the public. It will get back eventually to destroy and make more money, but it's all accounted for. So really, energy is this accounting scheme, right? Now, this is only for conservative forces, right? And we could extend this. Well, what we say is that the total energy of the system is given by its, let's say, the initial total energy is given by its initial kinetic energy plus its initial potential energy plus its initial kinetic energy. And its final energy, or the second time you measure it, it's just equal to the potential plus kinetic. And according to this equation, the initial is equal to the final. And it's equal to a constant, right? Now, this is what we'll be using to solve problems, because we can relate the potential energy to its speed, right? Because the kinetic energy is just equal to 1/2 mv squared, right? No matter what you study, it's equal to this amount, right? So let's look at a quick problem. So let's take a ball, let's say we drop a ball from a certain height. And let's look at it at three different this, and it travels down, and we'll also look at it halfway in between. Okay? Now let's look at the two terms. At this point, it's not moving. We're holding it in our hand. All right, and we drop it from here. So at this point, the kinetic energy, the potential energy is equal to mgh, and the kinetic is 0. It's all in potential energy. Halfway down, it's equal to mgh, and then its potential energy, its kinetic energy, is equal to V, which we can calculate, V2. And it turns out that, and then at the bottom, U is 0, and then it's all in the kinetic energy. And it turns out here, the kinetic energy halfway down is equal to half the final kinetic energy, because here the energy is split up between the potential and the kinetic. We would have to calculate V, of course, to actually show this. But it would be half the energy, right? And then here, E1 is equal to E2 is equal to E3. Okay? Now, let's do a few problems. So, let's say we have this problem. Let's calculate what V is over here, right? Based on this equation. So we have this equation. Let's actually calculate V at this point. So we have E1 is equal to E2. So MGH, so if we write it out, we can write it out like this. U1 plus K1 is equal to U2 plus K2. Now we plug in the terms. U1, the gravitational, is mgh plus 0 plus mgh over 2 plus V2. And let's solve for V2 here. So V2 here, okay, so I bring this to the other side. V2, all right, let's do this. This is equal to mgh over 2. I'm going to the other side. Let's multiply. Let's solve for it. So the 2's cancel out, the m's cancel out, and we're left with V2 is equal to GH. And when we plug this in here, it'll solve this equation, right? And this is just the difference between these heights. Okay. Or we can write it a little bit like this. In the book, they have it like that. This is example 0.3. So look how easy it was to calculate the velocity at this point. Think about what you had to do beforehand, right? You had to use the kinematic equation, right? You had to figure out, right? You had to do the velocity squared minus the initial velocity is equal to 2g times h, right? And here it's just this simple formula, right? Now, of course, once you include time and the kinematic equations would require solving a quadratic equation for time, then these really prove quite useful. So just by plugging it in, just by using this energy conservation, we can figure out its final velocity. We don't care about the acceleration or how long it falls for or what happens in between these points. We'll know the final velocity as long as we have conservative forces here, right? And well, as long as we have all the forces here. You can solve it without the conservative forces, which we'll go into in a second. You just got to account for the change in energy in that case. So let's look at the next problem. So let's go back to a roller coaster scenario. Let's say if we have a roller coaster, these are the supports, right? This distance to here is y. And let's say the roller coaster drops from this height. And it starts with initial velocity of basically 0, right? And in this case, we'll have E1, which is up here, or E initial. I like to use E initial, and E final, right? We drop down. Let's figure out the velocity at the bottom. E initial is equal to E final. Because there's hardly any dissipative forces. Assume that we ignore dissipative forces, right? And then in this case, if it's not moving, E initial is just equal to I initial. And then at the bottom, we choose this to be our 0 point. So we could set our 0 as this point. So at the bottom, there's no potential energy. And lost all its potential energy. And why can we say that that's 0? Because it doesn't fall, the cart never comes off its tracks because it never goes lower than this point. And what we really care about is the change in potential energy. So we could use this as our reference for 0. So then the final energy is just, it converts it all to kinetic energy. And then now we just plug in the formulas for gravitational potential energy and the kinetic energy. And we'll have mg y is equal to mv squared. V final squared, I should say. And this is y initial, right? And then from this, we solve. So then v final is equal to 2 times g times y. I'm just going to put y. Right? Or, oh, put y1. Okay? So that's where the final is. Okay. So the next part of the question is, at what height will it have half this final velocity? So it happens somewhere over here, and it doesn't happen in between, right? Because of the square term. So you're comparing a linear term, this y term, with a squared term. So it's not halfway in between, right? So let's figure out where it would have half this velocity. So we'll set it up, right? So let's start. So we'll use our initial position, and then we'll look at it over here, and we'll call that EM. We'll call it EM for middle. Okay. So EM would be mg. Ym, we don't know what ym, this is what we're looking for, plus mg vm. We know what vm would be. It's half of this, right? So let's plug that in. This is just 2. That cancels out with that 2. And we would have this, right? And we have this term. I just plugged the final 2 times, or half of the, I'm sorry, half of the final. The m is equal to over 2. All right, that gets rid of that 2. So we keep that 1/2 over here, right? Now we've got to solve for ym. Well, we know everything except for the exact quantity E. We didn't calculate, we didn't explicitly calculate it over here. So that's what we have to do. So we have this, and we get this. Now we have to relate it to E initial, right? And then let's erase this part. That was part A. So E initial is equal to EM. We could also use E final here. It doesn't matter, right? Because they're both equal to each other. Just B initial is E initial is easier because it has this it just has this MGY in it. So we have MGY1 is equal to MGYM MGY1 divided by 2. We only have now one unknown, ym, and that's what we solve for. Ym ends up equaling mg divided by mgi over 2. Oh. something here. Hold on. Shouldn't give me 1/2 of this. So we had this, and the final is equal to 2G. Oh, I see what I did. Okay. So V final is equal to this. So it's really over here, there should have been a 4. Or, yeah. So if this is V final, let's plug it in. Right, so then that would be, oh, let's plug it in. VM, I plug this in. Right, it's squared, so to take away the square root, and this is 4. So now we have 1/2. This is what I had before. Oh, that's what. Now you would have y 4. So then it would be a 4 over here because these two cancels out. So let's put that 4 in over here. And then this is equal to now mgy minus 3/4. So it equals half the height when it's 3/4 up, right? And that comes from that square that I messed up on a little bit with the terms. So now these cancel out, and we're left with the 3/4. So when it has half the velocity of the final velocity, it occurs at 3/4 of the height, right? So here's an interesting conceptual problem. Let's consider a frictionless slide. So this is 5. All right. So let's say there's 2 slides that Kathleen and Paul take. Kathleen takes this slide. I'll call her Kathleen. And then Paul takes this slide. There's no friction, it's only gravity. And the height is h. Okay. Who gets down? Okay, so at the end, what are the speeds? Of course, they're equal, right? Just based on conservation of energy. You know that the speed at the end will be equal, right? Now, if we're doing kinematics, we would have to take this whole path into consideration, right? You know, this would be a hard problem, almost impossible problem to calculate for Kathleen, because she's experiencing all these different forces due to the slide to either lift, make her not go down as fast, or to speed it up. We'd have to know the forces at each individual point, right? But since we know that there's no dissipative forces, and even if there were dissipative forces, it'd be easier. Because we just know the endpoints, the potential energy at the endpoints, we can figure out her speed very, very easily using energy conservation. Same thing goes with Paul. But this isn't the whole picture, right? Now let me ask you, who will get down the slide faster? Will it be the same? They end up at the same speed, right? Who would get down faster? Well, let's look at the speed at each individual point, right? So let's see how Paul travels. So he's going very, very slowly, and then he picks up all his speed at that last instant, right? So most of this distance that he travels, he's not going very fast. Now let's consider Kathleen. She goes, she picks up some speed, about a good amount, between a quarter and 3/4, right? She's about in the middle over here. And then she picks up the rest. So Kathleen's velocity, can't use the average velocity here. Her time average velocity. So instead of measuring the average velocity at each point, we measure the velocity as a function of time. Her timed average velocity is higher than Paul's, right? She's going faster most of the way down. And so in the end, Kathleen will reach faster because she's going faster over here. So she'll travel further, even though they end up at the same velocity. Right? It's interesting. You can read the rest of it on page 192 in the book. Okay. Now let's do a problem with the spring potential energy. Okay. So let's say if we had a toy dart gun. This is an example. Right? We have a toy dart gun that uses a spring to shoot the dart. Right? It has a suction cup on the end of it. Right? And this is the equilibrium point. Right? And initially, we load the dart gun. We load back the spring. It's held back by the trigger mechanism. And our initial energy in the system is this. We'll use initial and final here instead of numbers. Well, it's not moving, so this is equal to 0. And then if you remember the kinetic energy term, it's kx this. And this is loaded to 6 centimeters. So this is our initial kinetic energy. And then once we release it, and once the dart leaves the end of the gun, or leaves the spring, let's say we pulled the trigger and then it leaves the spring, right? At this point, as it leaves the muzzle, it's equal to this. We released all the energy due to the spring, so that's 0. So then we have 0 plus mv squared, v final, right? Now, let's figure out what that velocity is when it leaves the spring. So, all we have to do is set them equal to each other. K, v final, well, let me not skip steps. V initial equals V final. So then we have this, right? So we just solve. So V final, the 2's cancel out, is equal to K over M X. Right? It's equal to this. And then we could plug it in, all the numbers that they give us in this problem. The mass of the dart, M, the mass of the dart is 0.1 kilograms, right? And the K that they give us is 250 newtons per meter. So I didn't write this out in the beginning. It didn't really matter for the conceptual aspect of it. And then when we plug this all in and the distance, we get 3. So to figure it out. Now let me ask you, can we do this problem using the kinematic equations that we have? Right? Can we? What are the assumptions that we made with the kinematic equations that we've used for projectile motion? So the main one was that the acceleration has to be constant. The force has to be constant. Here the force is not constant, right? The force is equal to kx. That's a function of distance. So to do this using the kinematic, some kind of kinematic equation, we would have to derive it, and it would be a lot more complicated because of this x term. And you would only do this in the higher level courses. And there's a completely different method of doing it. It's called the Lagrangian. Okay. And then that's the end of this problem. So these conservation of energy problems are not very difficult, right? Compared to what we did in the past. Makes our lives easier. Let's do one more of these problems. Now let's compare what happens when we have two sources of forces. All right. So let's say we have a ball that we drop from a height onto a spring, right? Now it's interesting, right? So here we have let's consider 3 different snapshots of this. When the ball is just released, right as it lands, and then at the bottom. So there's actually something interesting. Okay, so we have this spring, right? Now we consider these springs to be massless. They don't have any mass. We don't have to consider any motion and anything that has to do with the spring, right? But think of this, right? So if this did have mass, right? Because of its mass, it would compress a little bit from its equilibrium position if there's no gravity, right? How do we take care of that? Well, it's a bit complicated, but in the end, it actually turns out that because of the mass of the spring or any mass on the spring, you could just use that new position that it compresses a little bit due to the gravitational force as its equilibrium position. You don't even have to take the actual compression into account. And this works quite well if you have a spring, if you have a hanging mass on a spring, right? It will extend a little bit, right? That new equilibrium position, you could just do the whole problem with that new equilibrium position. You don't care about how far it goes down. And we can do the calculations for that, but we won't, since it's a summer course. But just as a little knowledge. Okay, so let's consider the three scenarios, right? So the first scenario, right? So what in this system, there's two sources of potential energy, right? Gravitational and the spring, right? And we have to be careful how we define all the terms, right? So we'll call this distance to the top of the spring h, right? And then how much it compresses, we'll call that y, right? We'll call this distance y, right? Because this is where so in this region, you only have the gravitational potential energy, right? Up until this region. And this is where you have both the gravitational and the spring to account for, right? So let's figure it out on these two different positions. This is y1, y2, and then y3. Okay? And let me give you some numbers. The mass of the ball is 2.6 kilograms. The height is 55 centimeters. Y, this distance is 15 centimeters. And they ask us to determine the spring constant in this problem. What is the spring constant? Okay. Okay, so we have conservation of energy. We have two conservative forces, right? So that means that E1 is equal to E2 is equal to E3. And now we have to decide, what do we use for our reference point? Well, here, it actually doesn't matter what we use as a reference point. We could use this or this. But they asked us to measure all distances from the point, from the equilibrium position of the spring, from this point. So y2 is equal to 0. This is equal to negative large y, that's what they call it. And this is equal to h, right? So let's do this. So E1, we drop it. There's no kinetic energy. So it's all mg, the height from the reference point, h, right? E2, since we take this as our 0, the kinetic energy, so why don't we write this out? Let me write this out. So we have the gravitational potential energy plus the spring plus the kinetic. And in this case, we have mgh plus 0 plus 0, right? It's mgh. E2 is equal to 1, 1, 1, 2, 2, 2. And then here, mg, it's mg0, so this is 0. The potential energy of the spring is also 0, it's not compressed. And then we have this velocity over here. So it's all kinetic at this point. Then, when it's fully compressed, we have the potential energy to be negative mgy plus 1/2 kx y squared negative y squared, sorry, right? Plus its potential energy. And if it's fully compressed at this point, what's its velocity? Well, it compresses fully, and at this point, it stops. And then if we let it continue on, it'll spring back up, make the ball go back up to this height, and it'll just keep repeating this motion, right? So it's 0 over here. So then we have 3 terms, right? Let's look at this. We have, so if we follow this equation right here, we'll have mgh is equal to 1/2 mv squared and that's equal to mg minus mgy plus ky squared. Now, let's calculate. We're given h, so we don't know what V2 is. Well, let's calculate V2 from this 2 equality signs. So then V2 is just equal to the square of m2mgh, right? From the last equation, it still holds, right? This the speed when it reaches at this point. Now we can set this equal to this. So then now we have, well, the 1/2 cancels out. So we have G, M, H. Or, let me rewrite it into a better term. MGH, right? Now, if you notice, I solve for V2, and look what happens when I plug in V2 over here. It goes back to MGH, right? I didn't even need to use this to calculate V2, but I did it anyway to show you, right? Now, we set this equal. y. And they give us y, right? They give us y. So all we have to do is solve for k. So k is equal to 2 over y squared, capital Y squared, mg h plus y. Right? Now look at this. Even though we set this middle point to 0, we ended up with h plus y. What are we saying that with mg h plus y? Well, we're saying here that all the gravitational potential energy, when it's fully compressed, gets converted into the spring potential energy. Remember, we just have to bring this over to the other side. And I messed up with that. It should be 2y, that should be that. So this is just saying that we converted all the energy into gravitational potential energy into spring potential energy at this point. And then over here, what we did over here, we said we converted all the potential energy of the gravitational into kinetic energy, right? Remember how when we plug in V2 over here, we get back MGH. Okay? And I'll leave example 8, 9 to review at home. The swinging pendulum. So I will just describe it a little bit. I won't do the problem because we kind of covered it in the lab, and just review it at home in leisure. But a swinging pendulum and this problem sets up something quite interesting, right? If we release the ball and we let the system continue, if we let the ball continue moving, what will happen? Well, we drop it, it'll compress the spring, right? It'll compress all the way down, then it'll go back up, it'll shoot the ball up like I was saying earlier, and it'll come up to the same height and then drop back down and repeat the motion. And it'll keep repeating this motion over and over and over again for as long as the energy in the system stays constant, right? This is what's known as periodic motion, when this motion repeats itself. Right? So we use this to create motion that's periodic, and then we can measure how long it takes to repeat itself. And this is the basis for the original clock, right? You have this periodic, this system that has a conservative force where the energy does not lose any energy to the outside environment, or it occurs very slowly, right? And we can calculate the time it takes to repeat itself. You have a clock, a second, right? And the main system that's used for this is a pendulum because it's very easy to build. I never plugged in the numbers for this. Just look at example 8.8 this is example 8.8. So we have a pendulum, right? Now the pendulum swings back and forth like this, right? And it's a transfer between the gravitational potential energy and its motion. Here at the bottom, it has the highest kinetic energy, and it goes back up, and it's all potential energy. And this length over here, if this is L, this is L cosine theta, right? This is theta, right? And then this length, how much we move up and down, would just be the subtraction. It would be L minus L cosine theta, right? And that would what we'll use for the potential energy. Right? And please do this problem at home, and it'll swing back and forth, and it'll transfer its energy between potential and kinetic energy here at the bottom. Now, let's consider what happens when we don't have energy conserved. So how do we take care of that, right? So we had E1 is equal to the potential plus kinetic. And normally this would be, for a conservative system like we just studied, would be a constant. What if it's not a constant, right? Well, all we have to do, so let's say if it's not a constant, let's say if E2 is something else. Right? Well, and these are not equal to each other. They're not equal to each other. Let's say we have a dissipative force. The way we solve for this is we just include the work done on the dissipative force, right? So then that E1 plus whatever external work that's done on the system plus the work is equal to E2, right? If we put more work into the system, E2 would be larger. If we put less, E2 would be less, and that's how we account for it. So that means that the change in potential energy plus the change in kinetic energy is equal to all other forms of energy done on the system, no matter what it is. So all you have to do is account for all the other losses in the system. And if it's frictional, the energy goes into heat, or the motion of the molecules in the system. Now, let's say if I drop this from a certain height, right, and it hits the ground and stops moving, right? Once it stops moving, where does all that energy go? Well, it goes into sound, right? You hear the thing that drops, and you also heat up the object. So if you drop something from high enough, you'll heat it up. Think of an asteroid hitting a planetary body, right? It creates, it melts the rock, literally, right? It's extremely hot. And it's not from the heat that it picks up in the atmosphere, that's also dissipative as well, but it's actually from slowing down into the earth. And it kind of grinds all these molecules together, and it gives all that kinetic energy to the molecules themselves. Now the molecules themselves kind of move independently of each other, So in general, you don't see any translational motion. So the average motion of all the atoms together is equal to 0, but each atom has a lot more energy, so that the object heats up. So, and all we would have to do is just include the work that's lost due to friction, right? So if we had a system like this, right? Let's say we have a mass on the block M, right? And it's touching, and now it has some friction. And this is the initial point. And let's say we let it go and look at it when it's in equilibrium. This is some distance x, right? So let's compare the energy of these two systems. E1, we release it over here. E1 is just all kinetic, so it's kx squared. Over here, the system is E2, and its final energy is just this is all potential. This is all kinetic. V2, 1, 2. This is all kinetic now. And there's this dissipative force due to the friction. Well, let's figure that out. So it's a dissipative force. So we add it to, it's done, the work is done on the system, right? So we have to add it to E1. Well, it's taken away from the system. So we have to add it to E1. And this is equal to E2. So we move a distance x. So this is, so then we would just solve it. Or let's look at it a different way. E1 minus E2 is equal to W. Same thing as before. I showed you, I just wrote it this way to show you that the difference in energies between these 2 points is equal to the dissipative force of the non-conservative force, in this case, the work done by the non-conservative force, right? And so then we have kx squared minus m1/2 m v squared is equal to the work, and the work is equal to mg mu k, like this, right? It's just equal to the force of friction times the distance that we move, right? Remember that this is equal to F times L, right? And we move it an x distance. And this is mu mg times x. Right? So the change in energies is equal to the work. And friction is known as a dissipative force. And this is because it always removes energy from the system and puts it into heat. So it's a dissipative force. You know, you can have another force here that would add energy to the system. That's also possible. But that's it. Okay. So we're going to just read 8.7 on your own. We'll skip that for the summer course, and I just want to go over power very quickly. So what is power? You hear it all the time, right? What is power? You hear horsepower. You don't hear a car in terms of energy. How much energy does this car have? You don't hear that. You hear how much power does it have, right? What does it mean? Well, power is just how much energy that can be given off in a second. So the rate at which work is done, right? That's what we really care about, is how fast we can do the work. Well, partially what we care about, especially with a car, right? We want to supply all that energy to the car at once to accelerate it as fast as possible, right? So the average power over a given time is the work, the total work done in an interval divided by the time of that interval, right? And it ends up, and then the instantaneous power at any point is the change in work. So the change in energy of a system is how much power is given off or taken in. And then you can look at it like this. And then this is just the change in energy per change in time. So power is just how much work is done in a given amount of time, or how much the energy of the system changes in a given amount of time. Right? This is important, right? You know, to lift a heavy object, I have all this chemical energy stored in my body from all the things I eat, right? But to be powerful is to use all that energy at once to lift something up, right? We're expending all that energy at one time, right? That's why we say that somebody's powerful. He could expend all that energy all at one time. Like a turtle. Turtle has a lot of energy inside of it, right? Has, you know, carbohydrates that it can break down, but it can't use all that energy at once. So it's not, tortoise isn't as powerful, right? That's something that moves faster. And let's do one more problem. So let's do example 15. And here, let's say we have a car and it's at 10 degrees. And it's going up a hill, right? This car is going up the hill. We have let's do the force diagram. We have the normal force. We have the force due to gravity. And we have a retarding force. Now, the reason why we call it a retarding force, it resists the motion, and it's not just friction, it's also air drag, which is another form of friction, but we consider it differently. And these are the forces on the system. And not only that, we provide a force forwards by the car, right? And what they want to know is if the car is climbing this hill, it's 10-degree hill, at 80 kilometers an hour, how much power does the car have to give off to keep it going at this rate, right? And here, the retardant force is 700 newtons. The car is 1,500 kilograms. Sorry, 1,400. And let's figure this out. We need to calculate the force to move at steady velocity? Well, let's do Newton's second law. So Newton's second law states, right, for a constant velocity, there's no acceleration. So the force is equal to 0. The net force is equal to 0 in this direction, right? So the force that I have to apply by my car, I'll do car, is equal, has to be exactly equal to the retarding force plus the force of gravity pulling me downwards, which is the sine theta, right? Sine 10 degrees, all right. It's an undefined theta, right? And when we plug this in, right, the retarding force is 700 newtons plus 1,400 kilograms times 9.8 sine theta. We get a force of this, of 3,100 newtons, right? Now we're not done here. We figured out the force. Now we have to figure out the power, right? So the velocity of this in meters per second is 20, when we convert it, is 22 meters per second, right? Now let's look at our equation. P is equal to this, the change in energy. So what is the change in energy? The change in energy is the force is the work done by the object, right? Or energy, how much energy we expend is the work done by the object, right? So it would be, so let's convert the term for energy into, or let me write this. The change in energy is equal to the instantaneous power is equal to the change in work, right? So let's do that. Let's convert it. Well, the force is applied in one direction along the motion, so we know that the force and the direction of motion is the same. So it would just be F times, let's see what variable they use. F times, let's just call it X. Let's call it X times the distance that we travel. And it's the derivative of this. Right? Well, the force, the derivative of the force is 0, right? We have to do the product rule. So we have to take the derivative of each one, right? And then add them up. Well, and keep the other constant. Well, the derivative of the force is 0. It's constant, right? It's assumed in the problem. So it would just be the force times the derivative of x. What is the derivative of x? The velocity. So the power in this case is just the force times the velocity. And then in the end, right, this is the answer. And then in the end, we get, for this part of the problem, 91 horsepower. Well, let's put that in terms of kilowatts, 68 kilowatts. Right? And then, so that's for that problem. Now for part B, it's saying if it wants to speed up to pass somebody on level ground, so let's say if the car wants to speed up to pass somebody, right? And we have the same retardant force. And it wants to know the horsepower needed to pass somebody. And the car accelerates from 90 kilometers per hour to 110 kilometers per hour. Right? So the force that we apply, C, right, is going to be larger than the retardant force because we're accelerating, right? So that's just Newton's second law. So M is equal to A, our acceleration. This is equal to the car minus the retardant force. And we want to find out the force of the car because we want to calculate that power of the car, right? So let's calculate the acceleration. So the average acceleration is 110 minus 90, and it does that, and it takes 6 seconds to pass the other car. So then we divide it by 6 seconds by 6, right? A is equal to 3.2. Well, let's convert this to kilometers per hour, not kilometers per hour, to meters per second. And that would be 36.6 meters per second minus 25 meters per second over 6. And that is equal to 0.9 meters per second squared. Right? Now we have that. Now we know the acceleration. Well, let's figure out what the force of the car is. So we'll have A plus R, and this is equal to 2,000 newtons. And then the average power. And here, what do we use as the power or the velocity, right? Remember how it was the force times the velocity, right? The velocity is changing. So instead of using the instantaneous power, we use the average power. And here, the average power would be just the force. The force is constant times the average velocity, right? And the average velocity is the average velocity is equal to the average velocity is equal to 100 kilometers per hour, right? And then in terms of seconds, 100 kilometers per hour, that's it. 1,000 divided by it's 27, so V average is 27. We assume that it accelerates constantly, 27.8. So the average power is this. Let's see, and actually calculate this. Okay. So the average output power as it accelerates through is equal to this. And then this is watts. Now, what is the max power that it has, that it must output? Well, we just do it with the maximum velocity, right? The force is, let's assume the force is constant throughout. Acceleration and this retarding force is constant. Well, in that case, then the power max, the average power max is just 2,000 times 30.6 and this is equal to okay, and then that's the max power it needs to provide to pass the other power. Okay, so that concludes energy conservation. Please read 8.9, especially if you're in engineering, if you're an engineering major or a science major. It describes different plots of potential energy diagrams. So a lot of times we plot the potential energy or the energy of a system, right? So I guess I'll go over it now. So let's say if we calculate the potential energy of a roller coaster, right? Let's say if the roller coaster, let's say if we have this as the roller coaster, right? Like that. What will the potential energy as a function of distance be? Well, it's pretty simple. It's linearly proportional to this height. So it'll look like the same, right? If this is E, and this is H or Y, it'll look the same. It's just related by Y is proportional to E by mg, right? You just multiply mg by Y. Now, now we use this plot to describe the different energies of the system. Now imagine if instead we were looking at instead of a roller coaster, we were looking at some other system. We would look at this the same way almost, right? So, and there's different points, right? So over here, right, at this point, if we put the cart at this point, or at this point, right, the cart won't move, right, because the track is flat, right? The cart won't go forwards or backwards at that point. But if we give it a little nudge, it will move forwards or backwards, depending on which way we move it. So it's not stable in this position, and it will move away from this position, right? And then it'll go along here, right? If we put the cart along here now, and we gave it a little nudge, this way, what will happen? Well, it will push it up the hill a little bit, then it'll come back and it'll swing back around and back and forth, and if there's dissipative forces, it'll go back into the same position. This is called a stable equilibrium, right? Where a little nudge won't push it, won't make it fall out of equilibrium. And this is used all the time to describe phenomena, right? Like it's just all over. So like, think of a building. You want it to be in a stable equilibrium position compared to an unstable, right? Just used time and time again. It's also used to describe other systems, social systems, right? The way people socially interact. If they interact a certain way and then we give it a little nudge and then the whole thing changes. Or because of different social pressures, we'll go back to the same interaction. So this is used all over science. And if you look at these points, where the curve, instead of curving inward, it curves outward based on the second derivative. These are turning points in the system, right? And this is where you say that it has the maximum velocity. So read the rest of 6-9. It's interesting. It's important to know if you're in the sciences. So, okay, that concludes the lecture. Thank you. Have a good day. See you tomorrow.